So in this video, we're going to look at an example of a hypothesis test for the chi-squared goodness of fit, and also looking at chi-squared test for association. So this is the Chapter 7 worksheet. These problems are one of these two, the goodness of fit problems or the test for association. So as I go through these, I'm going to make sure to follow all these steps. I'm going to state the null alternative hypothesis in English. So for Chapter 7, I don't care if you write these down in mathematical notation. I think it's more important to write this down as an English sentence or two. I want to give the summary statistics, which is the test statistic, degrees of freedom, and the p-value. I want to make sure that each expected frequency or expected count is at least 5. I want to give the decision for the test with explanation. And then I'll give the conclusion in context. So the conclusion and the hypothesis should be in as plain English as possible. So the first example to look at, Eric wants to investigate whether the type of vehicle his coworkers drive are associated with gender. So kind of looking at vehicle preference, and does gender have something to do with type of car that people drive? And then a quick count of the parking lot. Eric compiled this data. So we've got different vehicle options, car, pickup, SUV, male and female, and we're going to use a 5% significance level to check Eric's claim. Okay, first thing I want to do is I want to write down my hypothesis for the null hypothesis. We assume there is no association between vehicle preference and gender. So for we're looking at a chi-squared test of association between two different variables. So the null hypothesis is always to assume no association between the two variables, and the alternative hypothesis is that there is an association between vehicle preference and gender. All right, so there's a null and alternative hypothesis. For tests for association, these are always the same. All right, give this summary statistics, chi-squared, degrees of freedom, and p-value. Okay, so I'm going to write down degrees of freedom is, and for this, it is r minus 1 times c minus 1. And r is the number of rows, not counting the labels. So that would be 2 minus 1, or sorry, 3 minus 1. I've got 3 rows right here, or basically 3 options per vehicle. And we're going to multiply that by the number of options for gender. Here it's 2, male and female, so 2 minus 1. So 2 times 1 equals 2. So we have 2 degrees of freedom in this scenario. All right, computing the test statistic, I'm going to go over to StatKey. So we go to StatKey and input this data to compute the test statistic. Excuse me. All right, so here I'm on StatKey, and I want to make sure you click on to find your test statistic. It's going to be one of these two. And for the first example, it's test for association. So chi-square test for association. I'm going to click on this edit data. Over here, I'm going to delete all that. So make this a little bigger. So I'm going to basically just try to copy down this table, male and female. And then I've got car, comma, 35, comma, 25. 35, 25. Pickup, 10, comma, 10. And SUV, 5, comma, 15. All right, I'll click OK. All right, and so just to see my table right here. For this worksheet, I just need this chi-squared test statistic, 6.666. But just to note, maybe on some of your homework, a couple problems ask about the chi-squared contribution and expected counts is right here. Okay, so I'm going to keep this up. The test statistic is chi-square equals 6.666. All right, I want to get the p-value. I can do this in any order, so I'm going to look at those expected frequencies first. The expected frequencies are the values here in green, so 10, 10, 10, 10, 30, 30. And that's because the male and female have equal numbers. So if we assume independence, they should be equal numbers amongst the different vehicle preferences, vehicle types. But I'm going to notice right here, note the expected counts are all 5 or more. All right, so we need to have at least 5 for the expected counts. To figure out p-value, I'm going to go back to stat key. I'm going to go to the main screen. And now to get p-value, I need to go to the theoretical distribution, click on chi-squared. Degrees of freedom was 2. Click OK. And down here, the chi-squared tests for chapter 7 are always right tail. So click right tail. And down here at the bottom, I'm going to enter that test statistic, 6.666. 6.666. Click OK. And here we get a p-value of 0.036. P-value is 0.036. All right, then we need to make a decision. Since p-value is less than significance, 3.6% is less than 5%, we reject the null hypothesis. The sample provides evidence that vehicle preference and gender. Since we reject the null hypothesis, I'm going to support the alternative. The sample provides evidence that vehicle preference and gender are associated. So do you want to make a note before we finish this example? We could say that they're associated. In some sense, that's a nice result, but it's really not that powerful. We can't say anything about males or females preferring one vehicle type over another. It just means there's maybe some connection between these two variables. To figure out cause and effect takes a lot more research, definitely generally a lot more difficult question. But that would be our conclusion to this hypothesis test. All right, in the next example, we have an investigation of top college hockey players. Let's reveal the following data on the distribution. So we've got hockey players born in January through March, 26, April through June, 22 players, July through September, 8, October through December, 4. Test the claim that top college hockey players are not born in each quarter of the year with the same frequency. And we'll use this significance level of 5%. All right, so I want to take a step back here. Let's think about what we're doing with this worksheet. We're looking at goodness of fit and test for association. I always think for test for association requires 2 questions or 2 variables. Goodness of fit is just 1 variable. So this problem, I just have 1 variable, the year or the time of year that hockey players are born. So I want to make a little note. This is a goodness of fit scenario. So for the null hypothesis, what are we going to do? We're going to test the claim that top college players are not born in each quarter of the year with the same frequency. So for the null hypothesis, we always assume something has to be true. We assume that top college hockey players, top college hockey players are born with the same frequency in each quarter of the year. The alternative hypothesis is that this is not true, and that at least 1 quarter of the year has a different frequency than the rest. So I think we can actually write this in mathematical notation. So I'll do both here, but I'm okay with just one or the other. So the null hypothesis is that the proportion born in, I'll say, January through March is the same as a proportion of those born in April through June, is the same as a proportion of those born in July through September. N is the same proportion of those born in October through December. I have 4 different groups, so those all have to be, 1/4. And the alternative hypothesis would be at least one of these proportions is going to be not equal to 1/4. So the null hypothesis is pretty strong. We're assuming they're all born the same quarter. The alternative is pretty weak. With our data, we might want to say that, the first 2 quarters of the year have a lot more hockey players, but that's not necessarily true, at least from this hypothesis test. All we could say is at least one is different. All right, okay, so summary statistics. I want to give chi-squared, degrees of freedom, and p-value. All right, so I want to note the expected counts for each category is going to be 1/4 times n, which is the sample size. All right, we're assuming they should be 1/4. So I've got 26 plus 22. Let's see, that's 30 plus 30 is 1/4 times 60 equals 15. So the expected counts are all 5 or more. Going with that requirement, we need to have expected counts of at least 5. So I should have 15 here, I should have 15, I should have 15. And the chi-squared tells us, gives us a nice measure of the difference between these. Okay, so I'm going to go to StatKey to compute the chi-squared test. Going in the main screen, I'm going to click on this goodness of fit. I'm going to click on edit data. Delete these. I'll say January through March. We have about 26. April through June. That was 22. July through September was 8. And October through December was 4. So type 26, 22, 8, 4. Click OK. All right. I'm going to click on null hypothesis just to note. I want to make sure that this matches up with our null hypothesis, and it does. The automatic setting in StatKey is to make these values, these proportions equal, but that doesn't have to be true necessarily. I got a chi-squared of 22.668. So the test statistic is chi-squared equals 22.668. And the degrees of freedom is, in this case, it's the number of categories minus 1, k minus 1. In this case, there are 4 categories minus 1, so 3 degrees of freedom. So with the test statistic and degrees of freedom, we could then figure out the p-value for this test. I'm going to go back into the main screen of StatKey, click on theoretical distributions chi-squared, 3 degrees of freedom, click OK. Always right tail for chapter 7 for chi-squared test. And down here I need to change this test statistic to the 22.668. I think it was, yep, 22.668. Click OK. And we get, I'm going to say this is a statistical 0. So p-value is statistically 0. It's not exactly 0, but it's statistically 0. So we will reject the null hypothesis. P-value is not exactly 0, but it's far less than 5%. This sample provides strong evidence that hockey players are not born equally in the 4 quarters of the year. All right. One quick note, this actually phenomenon happens quite a bit. And when people theorize that the hockey leagues start at a particular time of year, and the students that are born right around this time get more instruction just because they happen to be a little bit older at 3, 4, 5 years old. So a very interesting phenomenon happens in sports and academics.